deepest section of our workshop. It'll be all deep learning, all 3 talks. And we start with an appropriate title, and Zack Ives.
Thank you, Val. And thanks, everybody, for the opportunity to participate in what's been a really interesting, mind-expanding workshop. So, I kind of picked this title in part as a little bit of a pun. How do you put deep learning into the way we think about query processing? I should put a disclaimer. I'm not claiming in any way this is going to be a deep talk. But actually, I would love to get some early feedback and potential collaborations in a problem space that we've been just kind of starting to think about for the past few months, which I think is starting to yield some interesting problems. So I'm sure you've all noticed we're living in this interesting time where more and more of the data that people are starting to play with can feasibly be pulled off the open internet, whether you've got transformers or GPT or whatever. We're increasingly seeing things where it sort of makes sense to think about there being a database that we can analyze, but the database doesn't actually end up being the central repository for the data. Rather, it's more like a materialized view of stuff extracted off the open web. So, in a way, maybe the simplest, not as new abstraction of this is think of Google Scholar, right? So Google Scholar is a full-blown database. It's got the ability to do things with it. You could imagine if they made it fully available, and maybe Semantic Scholar is a better version of this. You could do data science type things. You could build dashboards. They obviously have a query and a search interface. You could really think of this as an SQL database. But of course, everything that's in it originates somewhere else. And I think the interesting question is, if we were to really embrace that model, right, where we have a thing that looks like a database, it's queryable, you can do stuff with it, but the data actually lives elsewhere and is extracted and linked today based on embeddings, based on other learned measures. What would such a system look like, and how do we actually make it perform well? And I think a lot of my interest has been, can the ideas of query optimization, view update, view maintenance, etc., actually make sense in this kind of new world? Of course, in keeping with the themes of this workshop, also there is lots of interesting opportunities for thinking about provenance. Okay, so just to give a few examples of some very simple use case queries that we might come up with in this broad space, you could think of very simple kind of selection queries. I have PDF papers, and we have a transformer that extracts out titles and authors and venues and citations, right? And generally, we tend to think about it as some black box user-defined function. But part of what will come out is not just the tuple, but probably some kind of label or class prediction or whatever. And you can actually think about there being kind of a threshold somewhere in your query, which is like, only do this if we think it's accurate up to some confidence level. Okay, we can have more general versions, right? There are actually a ton of places where people seem to monitor social media for mentions of their products or their favorite celebrity or what have you, and build dashboards and so on. I guess probably more if you're a publicity person or something like that, where you might be monitoring, well, I guess I can't say Twitter anymore, X, and Facebook with different extractors that do kind of the same thing. Again, you can union things together and produce a result, and we might actually want to think about provenance now, because did this come from Twitter or did it come from X? And maybe the more interesting one, I'll touch on this late at the end, might be something that's not even in our normal database comfort zone. Think about situations where we have security monitoring and video frames. Well, now we have the ability to deal with these through embeddings. So imagine you take video frames and you want to actually preserve privacy of the folks who are supposed to be in the lobby. So we detect all the faces in the frame, we convert them to embeddings. Now we do a similarity join with the faces of people who we know. And actually we go back and basically take those images and blur out everybody who's supposed to be there, and we only get to see the folks who shouldn't be there, right? There's lots of these kinds of applications that you can come up with, and you can see each of them is kind of, again, I'm picking simple examples. They're basically, let's say, unions of conjunctive queries with some ML components somewhere along the way. Okay, so that's the space we're interested in. Of course, the first question is, if you're going to put all these things in, how do we sort of generalize, let's say, a streaming database query model or even a standard relational model to deal with this? There are lots of different approaches. In fact, I think I don't see, at first glance, I don't see Meyer here, but he'll probably talk about it. Oh, sorry, there we are. He'll probably talk about different formalisms for this. But basically, there's a question of how do you combine tuples and tensors and vectors. I'm going to claim that the way that we want to do this is just to think about a standard relational model where we add a tensor data type, and then you have to think a little bit about adding some extra algebraic operations. But basically, at some level, pandas already has these, so we can, more or less steal these things for moving between fields and vectors and exploding things and nesting them and stacking tensors and so on. Okay, so broadly for the rest of my talk, I'm going to sort of assume we have this extended algebra and sort of see what we can do. And our interest is really in this question of, okay, how do we do efficient query processing? Again, I'm going to think of both updates and queries in this model that sort of combines what we know from structured queries like constraints and algebraic equivalences with these sort of more numerically generated machine learning stages with tensors and dot products and activation functions and so on. And ideally, there's some synergy between the two that we can exploit to get better performance. Okay. Now, there's lots of different areas you can look at. Mayur and I have talked at various points, and certainly I've read a lot of his papers, and there's this whole interesting area coming from sort of outside the DB community called neurosymbolic reasoning. And deep problem is another example of a system in this space where I would say, like, at least what I have interpreted from the community is the focus very much is that by putting these things together, you can learn better and do better predictions. Okay. The part I'm interested in is, suppose we're just mostly focused on the prediction side, can we actually do updates and maintenance and so on a lot better? Okay. So we want to basically go into the neural network and break it into its individual components and hopefully get some synergies by thinking about that. So again, I'm going to expand my set of operators. Again, not inventing anything new. At some level, PyTorch and TensorFlow and all of the other kind of deep learning toolkits already have this data flow graph type model with various ways of connecting neural network activation units and scaling data and so on. So we're going to expand our vocabulary with those and then start to look at queries. Okay. So this is probably about the simplest version of a query I can come up with that has a neural network component. Suppose we have a conjunctive query. It produces a set of tuples. So I'm going to show a tuple as having, let's say, 3 fields like this. That'll feed into the neural network model. It will produce a label, which we're just going to add as another field because we want to be able to expose this to our query language. Okay. And of course, that's one version, but a more interesting version might be, well, my tuple comes in with provenance, and I want to propagate that through my machine learning model and actually create the label and have some kind of provenance on the output. Okay. That's not really the end of the pipeline. In general, we're going to have some additional relational stuff, maybe at minimum some selection threshold for confidence on one or more classes. Okay, so this is probably the simplest query that we can come up with, and I'm going to use this as a little bit of an example to sort of show some of what we can do, and also, I guess, exercise PowerPoint's fancy transitions. So this is the same query, but I've kind of rotated it 90 degrees so we can drill down. So again, I have a relation down here. Let's suppose that it's maybe R join S. It's got a sequence of tuples. We're going to feed those one at a time into our machine learning model. We're going to get out labels that will concatenate onto the tuples. Within the neural network, again, we have a set of things that looks very much like our familiar relational operators, but they all work on vectors and tensors. So roughly speaking, what will happen here is we'll take each tuple and actually feed it into different layers in the neural network. This is, I will say, not a deep neural network, but pretend that it is. We have 2 layers here. So each tuple, if its features were numerically valued, what will happen is we will multiply the feature values by the weights for one of these activation units. This is just a dot product. And then normally the output gets mapped into some subset of possible values. So what ReLU does is basically it truncates negative values at 0. We will often feed the same data into multiple of these in parallel, because each of these will essentially will learn different combinations of the features and predict some higher level, basically derived feature. And this continues sort of through the neural network. At each level, we're doing a dot product followed by some particular function. Okay, so I think that is what's called feed forward in a neural network in the simplest nutshell. Now, one question is, how do we want to think about tuples that go through this, especially if we have provenance annotations on the originals? What should the provenance on the outputs be? There are lots of ways you can think about this. The way that we have modeled the neural network is to really think about it as kind of a external user-defined function and essentially model it more or less as doing a dependent join with some external relation. So the neural network is some other relation. I have bindings to my features. I send it over to the neural network. I get back a set of tuples that get joined with the input. And if I do that, then I can get provenance to be some product of the provenance expression of the original plus, well, times some function symbol over whatever went into the neural network. Okay, so that's kind of how we think about provenance in this model. Now, so far, we've just produced the output of a view. There's an interesting question, of course, of how do we let end users correct the fact that there's a lot of likely gibberish in the views? And the simplest way to do this, which I'm only going to sketch, is to do some kind of incremental machine learning. And the way this typically works is, you make a prediction on the output here, which is y hat. This is my label. It is wrong. Let's say the user says, delete this or change its score or whatever. So normally you'll compute a loss, which is a penalty for being wrong, and then propagate that loss back through the neural network. And actually, this is my one slide connecting to semi-rings. There's very nice work that I first became familiar with through Meyer's work on Scallop, but dates back to Jason Eisner, who was building a system called Dyna for natural language processing and weighted finite state transducers with a thing called a gradient semi-ring. And the idea here is provenance becomes this pair of a score and a gradient vector, and they define a set of operations for the plus and the times like this, where you can add the probabilities and the gradients for the sum. You can multiply the probabilities, and then you do the product rule when you multiply the gradients. And this effectively captures exactly what PyTorch does today in this thing called autograd, where whenever it makes a prediction, it logs the gradients so that it can do stochastic gradient descent. Okay, so again, this is not going to be the focus of my talk, but somewhere that will happen. What my students and I have been interested in is thinking about now, given an update, we have this view. How do you actually compute or recompute the results of the view? Okay, and what we've convinced ourselves, which I hope might be something of broader interest, is there are opportunities for taking ideas from relational current evaluation and applying them in this context. So the first thing I want to show you is a kind of a special case of sideways information passing, where we can actually make the processing of the data through the neural network much faster or more efficient. And then the second thing is really thinking about what it means to have equivalences when you have a neural network in the middle. Okay, so let's come back to our simplified illustration of a tuple going into a 2-layer neural network. I've slightly simplified the version from a couple of slides ago, but this is basically the same thing. I take a tuple, let's say it only has 2 features now. I'm going to run it through 2 activation units where the tuple will get multiplied by the weights. We do ReLU, we take the outputs as 2 features, we weight those, and then we do a sigmoid function at the end. Okay, so this is slightly simplifying things. I'm removing a few details just to focus on the gist of the computation. Okay, so here is, I think, the interesting opportunity here. If you look at this kind of a query, almost always we have a label with a numerical value, and we're going to have some threshold here before we count it as being interesting or belonging to our class or whatever. So the question is, can we essentially do a sideways information passing type idea to take this constraint and what we know about values throughout this thing and compute thresholds to prune the processing through the neural network, right? In many ways, you know, if you're familiar with Fagan's algorithm and the basic notion of trying to threshold or bound all of the data that you haven't seen, our insight is that you can do similar things with a neural network in this relational setting if you are allowed to do a little bit of setup in advance. Okay, so basically, what we need is a way of putting a bound on all of the data that we haven't seen, or another way of putting it is we would like to propagate data through our neural network in monotonically decreasing order of score. Okay, so that's the basic idea. Again, it's very much like what the threshold algorithm does, but we're not looking for top K, we're looking for anything above max threshold. Yes?
You set up like the weights are fixed in the network?
Okay, so generally speaking, the weights are fixed until we do a cycle of SGD, and then and the key is when we relearn the weights, the question is going to be how do we recompute all of our output. Now, most likely, if you update the weights, you only change them in a small amount. So most likely, the set of instances in the view is almost the same, right? That's what we're intuitively going to rely on. Yes?
So the provenance at the end takes into account the whatever the sigmoid functions? Or is it
Yes. So okay. So
you have to assume that the sigmoid function is well defined on the semi-ring, or is it only for the non-negative weights?
okay. So okay. Let me see if I can. There's a bunch of details that I'm going to kind of postpone, but basically, if you go back to that gradient semi-ring that I hinted at, that is going to essentially, one way of thinking about it is it logs the derivative of the sigmoid at the point that I made the prediction.
This went to some particular semi-ring.
That's right. Yes. Yes. This is not a. In fact, this is one of the interesting questions that we might want to talk about after. Okay. Okay. So we're okay. Yes, Joe. Yeah.
For ranking top K type of stuff,
Yeah.
why do we have competing candidates of output here? I'm not even seeing that.
Sorry. Competing candidates. Okay.
Suppressed by other potential outputs.
No. Okay. So let me restate the problem. I have a large set of tuples. Say 1% of them are going to be interesting events.
Okay.
Okay. So I want a pruning strategy where I don't have to look at all of them in order to find the 1%. Does that make sense?
So, but is the threshold rank based or is the threshold sort of metric based?
Okay. This threshold is metric based, and we haven't yet gone into the example, so it might become more clear when we do the example. But basically, we have a hard threshold. We will, however, want to set things up in a particular way that we can read the data in a monotonically decreasing order in general. Okay, so the idea here is I take my table, and I'm much like, again, with Fagan's algorithm, I can build some unclustered indices on the table. I'm going to pick a subset of the features that I think are important. And basically now I can read all of the results of T in decreasing order by F1 or by F2. Okay?
And there's a combination of these metrics coming in that lead to.
Yeah. So why don't I go through the example and we can see if it makes sense. Okay. So I've set this up in a way that's slightly simplified, but let's pretend that those details aren't there. So the basic idea is I have a set of weights. These are already set from training or initialization or whatever. I have a data set that I'm going to be continuously going over so I can pre-index it. Okay? And I'm going to pre-index it by F1 and F2. And so I'm going to just draw this as, so here's the key, 99, and here's the whole tuple, T1, right? And so T1 has values of 99 for F1 and F2. That will be the highest value for F1 and the highest value for F2. Okay. Again, if you're familiar with Fagin's algorithm and you're reading in stream monotonic order, same idea here. Okay. So when I do this, right, what will happen is I'll take this T1 tuple, which I've seen in both places. I will propagate it through my neural net. At the first level, I will multiply the 99 by 0.5 and add 99 times 0.3 and the ReLU, which for a positive number will just pass it through. Okay. At this point, I know there's no value of T1 with a value of F2 greater than 99, and same for F2, but I also have a bound on the output of the ReLU because the weights are fixed and positive, and my data is monotonically decreasing. Okay. And I can do the same thing on this side with the same tuple through the second activation unit, and then propagate it up. And this is above my 0.9 by a tiny margin, so all is good. Okay. So now the question is, how many more tuples do I need to read before I can be convinced that there's nothing else that's going to score above 0.9? Okay. So I will consume from my index. The next one, let's say, is 88. This gives me an updated bound on this value because it can't be more than 88 plus the 90, well, scaled 88 and 99. And also it updates this value. And I can keep reading until I get additional tuples that show up in both indices. And then I propagate them. Now I know there's nothing bigger than 15 here and nothing bigger than 28 here. And if I propagate this through, these are already below the threshold. And basically, by reading 3 tuples, I have skipped huge portions of my data set, and I don't even need to run the classifier on anything for most of these. Okay, so that's the basic idea. Yes?
That the weight are only positive is a strong restriction or no?
Okay, that's for the example, but there is a generalization, yes. In fact, why don't I just slightly elaborate on that? This is a sketch of the basic algorithm. In fact, so first of all, your weight could be negative, in which case you have to go in the other order. And the more interesting thing is you could change the weight where it started positive and then it flipped negative or vice versa. Okay, so there's some details, but by and large, you can use this thresholding and sideways information passing idea in a neural network and actually, get the benefits of standard database queries plus neural networks with database style techniques pretty well. Okay, actually my former student Peter Chen ran this and then said, okay, let's compare it to PyTorch with a GPU. Guess what? All too often, PyTorch with the GPU still won because it was doing like 5,000 times more work, but hardware is a very powerful thing, right? So sometimes the GPU still wins, of course, using a lot more energy. But the interesting place where essentially we found we always won is this view maintenance version of things. So I computed the output once. Now I do some minor weight updates. Now I want to recompute. So basically you take all the things you previously outputted, you re-update the scores, and you might have to throw a few away because they no longer satisfy the threshold. Then you just read enough additional tuples under the new scoring model to potentially satisfy the new threshold, and you're done. Okay. So again, the main idea here is this is, to my knowledge, the first time we've actually managed to put these two ideas, kind of a database style constraints and kind of neural network feed forward into the same framework and actually get some pretty meaningful benefits. Let's see, how am I doing on time? Probably need to finish soon, so I'll just say our results, even against PyTorch with the GPU, we got up to 8x speedups when the number of members of the class was, up to 10% of the overall data, which we think is actually quite realistic for many kinds of extraction and event detection stuff. You're not expecting 50% of your data to be an interesting event, right? Okay, so sideways information passing actually can be integrated into deep learning to big benefits. Okay, I want to just tease one other idea that took us a long time to come up with, which was thinking about query expression equivalence. Okay, so here's our setting, the kind of video processing version that I talked about. We have a video stream coming at 15 frames a second. You want to process the data, extracting faces, computing embeddings, and seeing who's in the frame. Okay, actually, the speed of this pipeline is going to vary tremendously between there's no faces in the frame to suddenly there's a crowd. Right, now if you have some kind of latency or throughput guarantee that you need to have, like you keep up with the video frame, we have a bit of a problem. Okay, so what we would like to do is take advantage of the fact that you can build different classifiers that essentially do the same task. Right, I think the problem that at least we wrestled with for a long time is, what does it mean for two classifiers to be equivalent? What does it mean for two query subexpressions with a classifier to be equivalent? And I think our conclusion ultimately is that actually doesn't ever happen. You take the same neural network and you train it with different random initialization parameters and you get different performance. So it's not so much you can actually say they're equivalent, but perhaps they're sort of functionally equivalent. And perhaps you can create a total or a partial ordering on your preference of them. And of course, you have different performance characteristics for each. So with that basic observation, it's possible to actually come up then with ways of switching between alternative classifiers and so on, even in an adaptive way. So actually, very much based on Joe and Ron Avner's work from, I think it was 2000, right, on eddies, we tried to take a similar approach. So basically, you want to use your most accurate classifier as much as possible. But when it starts to get oversaturated, you want to turn on and potentially flip to a faster but less high quality classifier. But you also want to flip back the moment that you can. So basically taking many of the ideas of eddies, the idea here is we have kind of our pipeline that does the accurate neural network. There's a queue in front of it. We have kind of a router in front. As frames come in, if they start to pile up after some threshold, you enable an alternate branch. And now you have a randomized strategy that prefers queues that have less load in them, and you'll kind of randomize across these things, preferring the ones that are faster, but still using the slower, more accurate one where you can. And eventually, when things kind of clear out, you'll actually disable the one you don't prefer and move forward. Okay, so that's our basic idea. The main thing here that I found to be personally gratifying is the notion of equivalence is sort of fundamental to the way we think about the world. And it just really doesn't actually work in a classifier world, but there are alternative ways we can think about this. So let me wrap up. Val said I had now probably a minute and a half left. I think this problem of trying to build maintainable, updatable views over the results of machine learning plus queries provides a really interesting test bed. I do think there are lots of applications that look like this today, and people are just batch rerunning the whole thing and not allowing them to be updated. That isn't the way the world should be. There are connections to provenance here, view updates, sideways information passing, equivalence, and so on. Would love to talk more. This is really just first early steps in the space, but I think there are lots of connections and lots of ideas that have come through the last couple of days. I will just put up, in wrapping up, a few of the open problems that I think are quite interesting in this space, one of which is this gradient semi-ring model. I think it's quite interesting that it captures enough information that you can propagate updates backward through and kind of blame each input unit accordingly and actually get something that's well formed. I wonder if there are generalizations of that idea that make sense in other query contexts. So with that, I will stop and happy to take any questions. Thank you.
Okay, we're done for
One question.
So right, so this Fagan's algorithm idea there, right? This would only work, right, if there is some kind of linear property that the network behaves linear in this one dimension, right? That I can just increase. It couldn't be something like where a higher value I go lower, and then even lower I get again a higher score, right? And that's not guaranteed, right?
Sorry, which part? Okay, so there's several different aspects here, right? So if I'm using a neural network, generally I will have dot product as my first function here. Now what I'm relying on is the activation function also is, for at least certain parts of the range, also monotonic in the sort of Hagen sense. So ReLU, actually for negative numbers, you kind of have to ignore that, but that's actually a place where neural networks don't work. Anyway.
Well, I mean, basically the ReLU makes it powerful, right? Without the ReLU, I just have a linear model, right?
Yes, although again, sigmoid, I always have sigmoid as an option, right? So anyway, I guess what I would say as succinctly as I can is, I think if you look at least all of the neural network setups that I have seen in the general case, they satisfy the properties that we're relying on.
So that they are monotone in each dimension, in a sense.
Again, the basic building block in the neural network is this linear combination of features, right? So that part is, yeah.
But I mean, there might also be negative weights in there. But if not,
actually, the algorithm generalizes that. So you basically you have to flip your read from smallest to most negative to most positive, and so.
Right. So now for the linear part, I think I agree. But I have to think. I don't understand why it works for right, basically activation function that is whose purpose it is to make it non-linear, right? Because otherwise I couldn't start with a linear model.
Okay, note that it's usually the composition of the linear functions that I'm relying on especially, right? ReLU is linear for half of its domain, right? It's just, truncated 0, otherwise linear.
Basically, then you're saying I can replace my neural network with a linear function, right?
No. At each level, I have to recursively do this threshold thing.
Oh, each level.
Yes.
Okay, good. Does
that make sense? Okay, cool.
Okay. Thank you very much. So we're gonna go again.